So this video is going to give you a briefing and background to the pharmaceutical analysis experiment. So what you're going to be doing in this experiment is you're going to be given an unknown sample in the form of a white powder, and what you've got to do is use a couple of analytical techniques to work out which of these three possible compounds you have. Is it aspirin, ibuprofen, or paracetamol? And by doing this, you will be sort of learning how to perform a couple of standard techniques that we use to analyze the structure of organic molecules, which most drug molecules are. And the skills you're going to use to do this will be thin layer chromatography and infrared spectroscopy. So as part of your pre-lab exercises, we have videos that show you how to perform TLC and IR. So please do watch these before you start the experiment. They'll ensure that you are you go through the experiment much more quickly. Everything will work a lot more smoothly for you in the experiment if you do this. Now what I'm going to do is explain to you how thin layer chromatography works, a little bit of the background theory behind this technique. And actually, thin layer chromatography is kind of very similar to paper chromatography, where you might remember sort of putting a piece of ink onto a filter paper, letting water run through the ink, and then you see the different the different colours that make up the ink sort of separating and travelling up the filter paper and separating out at different rates. Well, thin layer chromatography is very similar to that technique. The principles are basically the same. It's just a variation using different materials, and it's just more specialised and focused on use for the analysis of organic molecules. So what you have first is you have a TLC plate. It's a plate that's made of silica gel, and I've got the zoom in there on the structure of silica. It's a polymer with silicon, and key things here, we've got these polar OH groups. So this is what you use instead of the filter paper in that classic pen and chromatography experiment I explained before. And what you do is you place your compound at the bottom of the TLC plate. So your unknown sample, and then also in this experiment you'll also have some known aspirin, paracetamol and ibuprofen as well that you'll be putting on your TLC plate. Then what you're going to be doing is you're going to be placing it in a TLC tank. So you place your compounds on the plate. You can see that TLC plate there goes into the beaker, which is going to act as your TLC tank, and you have some solvent, some organic solvent in the bottom of the TLC tank. So this is the solvent you're going to be using instead of water that you use with the felt tip experiment. You're using an organic solvent here instead. And what will happen is that solvent will run up and travel up the plate. The plate will soak up the solvent and it will run and draw up the TLC plate. And just like when you do the experiment with water and the felt tip, you get the ink running up the filter paper. These organic compounds, those pharmaceutical drugs, will run up the TLC plate, and the rate that they run up the plate will be dependent on their chemical structures. Okay, if I go back to the first slide, you can see each of these three different pharmaceuticals have different chemical structures, which means it will run up the plate at different rates. So the reason why some compounds run higher up than others is down to the structure of the silica here. Okay, these OH groups are polar functional groups. They can hydrogen bond with themselves or with the molecules that are running up the plate. So if you've got a molecule with polar functional groups, then they will stick to the silica, to the stationary phase, quite strongly, and they won't run up that high. If you've got a non-polar compound where the interactions are much weaker, with the silica, then they will run up much higher on the plate. And I've got an example of that here. Okay, we've got two organic compounds. One's got a OH group, one's got a ketone. Both are a little bit polar. With the CO bond has a dipole, the OH has a dipole as well. However, the OH bond is a stronger dipole and it can do hydrogen bonding. So it runs up the plate. It sticks to the silica much more strongly. It doesn't run up the plate as high, whereas the less polar compound will run up higher up the plate. Okay, so what we can do is we can actually work out which of your unknown compound sort of belongs to one of these three compounds, because if on your TLC plate you put your unknown sample and then you put those other three compounds, ibuprofen, aspirin, paracetamol, the unknown compound should run up and match the level to one of those other three pharmaceuticals, and whichever level it matches will be the compound that it should be. Okay, so that's how we can use thin layer chromatography to work out which one of those three compounds your unknown sample is. It's a very standard technique for analysing what you have, what compound you have in organic chemistry. The next technique you're going to use is infrared spectroscopy. Now, as you can see here, we've got an animation, and what that animation is showing is how the bonds between two atoms move. They can actually stretch out, and which is caused by repulsive forces, and then when they get so far, they come back together from attractive forces. So these are repulsive forces between the two electrons in the atom, and the attractive forces are between the electrons in one atom and the nucleus in another atom. Okay, so play that animation again. So what that causes is it causes bonds to vibrate. Okay, and all molecules do this. They vibrate along the axis of the bond, and this vibration has an energy, and the energy corresponds to the electromagnetic region of the spectrum. And so what we can do with infrared spectroscopy is we can work out what bonds we have in our molecules, and therefore work out what structures these molecules have, because depending on the type of bond that they have, they'll have a different energy of rotation, but will all be within the infrared region. Okay, so again, we'll go back to the structures. Okay, the typical bonds that you can see vibrating in an IR spectrum, okay, will be things like CO double bonds, OH bonds, NH bonds, for example. Okay, and you can see that these molecules have some of them, those types of bonds, but there's some are different to others. So we can use this technique to work out which of these three structures you have. So what happens is if you take your molecule and you irradiate it with infrared light, the bonds that are vibrating will absorb the radiation that matches the frequency and the wavelength of that vibrating bond. Okay, so here what we have are, they look like troughs, but we call them peaks. Okay, and each of these peaks corresponds to the bonds that are vibrating. So when we have OH bonds, for example, in a molecule, they vibrate around about this region here, about 3000 wave numbers. And if we have a CO double bond, it vibrates around about 1750. Okay, so what you're going to do in this experiment is you're going to run an infrared spectrum of your unknown sample. Okay, and you're going to look at where the peaks are, okay, in the IR spectrum, and then work out what bonds you've got. And based on what bonds you've got, and sort of matching it up with the information from the TLC, you'll help you work out what the structure of your molecule is and which of those three compounds your unknown sample is. Now, when we analyze an IR spectrum, we have lots of bonds, lots of peaks below 1500, which corresponds to like single bonds, that are vibrating, that have got atoms of roughly similar mass, like COs, CCs, CNs. We don't tend to sort of analyze the bonds in that region because organic molecules will have lots of those different types of bonds. But what we're really looking for are the kind of key bonds that you get sort of above 1500, and they're very typical of the key functional groups that you have. So have you got carboxylic acids? Have you got alcohols? Have you got amines? Have you got amides? IR will help you be able to work that out. Okay, so then once you've done these two sort of techniques, and you've worked out your unknown sample, you'll then sort of show your TLC plate, your analysis of your IR to a demonstrator, and tell them which of those three compounds you think you have, and then this will get sort of used as your sort of assessment for the experiment. Okay, so there's nothing for you to do afterwards. It's just complete the experiment, get your data, analyze your data, and work out which of these three compounds you have. Okay, so that's the briefing and introduction to this experiment.